guys, hi and welcome to our first lesson in, I guess 2 weeks. Hopefully you felt good about your test last week. If you also haven't gone ahead and done all of the terminology in that learning assignment that I've set, then you may want to go back and do that just so that you're super clear when I'm using certain terms through this, that you know exactly what I mean. I want to talk about some resources you're going to want to make sure that you have nearby as you move through this unit. As always, you're going to want your periodic table, right? We know this. We're actually going to talk about it a little bit today. I also gave you a reference sheet that looks like this. It was a very bright color. I can't remember if I did it pink or green for you. Hopefully it's in your binder. As always, we need the polyatomic ions, but on the back, we're going to start using this solubility chart. Now, if you don't have this sheet at home with you, that's okay. I've also put it not in our weekly folder, but in the solutions unit folder overall. I put the reference sheet there. It also can be found on page 363 in your textbook, and you will need to refer to this. So I don't know if you remember, but when we were doing some reactions, I would throw the state symbols on and I'd say aqueous or solid, and I'd make a comment saying, I'll teach you how to figure it out later. Well, this is me teaching you how to figure it out. Okay? So when you go through this, you're just going to read through and look for the anion. So for example, if you had calcium fluoride, well, I'd read through, there's fluorine. I see that calcium has a low solubility. So that means anytime I see calcium fluoride, it will be a solid. It won't dissolve into a solution. Most other fluorides, other than these four, are soluble. So if I was looking at maybe magnesium sulfate, scroll down, I see, okay, sulfate. I see that calcium, strontium, barium, and lead sulfate are all low solubility, but all others are soluble. So if I had a solution with magnesium sulfate, it would be aqueous. So just make sure you have this handy, whether textbook or the actual reference sheet. Today, we're going to talk about factors that affect solubility. Some you may already know, some you don't, but we also need to differentiate between solubility and rate of dissolving. Okay, so let's get into this. When we start with this, we need to look first at sometimes molecular is different than ionic solubility when we look at these factors. So our first factor that affects solubility is forces between particles. And within this, we need to look at ionic compounds and molecular. We're going to do ionic first, as I'm sure you figured out by me writing the word ionic. So ionic compounds, we need to look at ionic charge and ionic radius. You might see it referred to as ionic size in the textbook, but we're better than that. So when we look at ionic charge, a larger ionic charge will result in a lower solubility. For example, if we look at a solubility of an oxygen ion, it has a solubility of 0.0006 grams per 100 milliliters at room temperature. If we look at the solubility of an iodine ion, we see that it has a solubility of 0.008 grams per 100 milliliters at the same temperature. All right, so looking at this, well, this is over 10 times more soluble than this ion. So when we're comparing two different types of, two different ionic compounds, we need to look at what the ionic charges are. I'm just going to white this out and we'll do a couple examples for together. So for example, which is more soluble? Would it be potassium chloride or potassium nitride? Our cations are the same, so that's not going to cause a difference. So let's look at our ionic charges. We see chlorine has a charge of -1. Nitrogen has a charge of -3. This greater ionic charge means that it's a lower solubility. So potassium chloride will have a higher solubility. Lower charge, therefore higher solubility. Let's do another one. Which is more soluble in this one? How about magnesium fluoride? Oh, not magnesium. And sodium fluoride. Let's look at the ions. Here, our anions are the same. It's our cations that are different. So magnesium ion has a charge of +2. Sodium has a charge of +1. Okay, again, lower charge means a higher solubility. The other piece that we need to look at with ionic compounds is the ionic radius. And here, a larger ionic radius will increase solubility. And these make sense if you think back to how these forces are going to interact. A greater ionic charge means that more electrons are being exchanged, right? So when we dissolve an ionic compound, that's called dissociating. It breaks the ions apart. A higher charge means that's more work. With an ionic radius, there's more distance between the two particles, so it's easier for that electron transfer, right? That's going back to that electronegativity piece as well. How do we know about ionic radius? Well, that's when we're going back to our periodic table, right? Remember that ionic radius increases as we move down the periodic table, obviously because we're adding a shell of electrons each time. Atomic radius decreases as we move across a period, and that's because of that effective nuclear charge. We have more protons, so it pulls, I'm sorry, you can't see me talk with my hands, it pulls all those electrons around the nucleus in tighter because it's a stronger force. Okay, so if we compared some here, so for example, which compound has a higher solubility? Let's compare magnesium chloride with magnesium bromide. Now here, we see that they have the same cation. We can't separate that. We see also that both of these anions have the same charge. So we can't compare that. What we can do is take a look on our periodic table between chlorine and bromine and say which one has a higher atomic radius. It's going to be bromine because it is lower down, it has more energy shells. So magnesium bromide has the higher solubility because it has the larger radius, and it's bromine specific here, therefore higher solubility. And that's what we're looking at for ionic compounds. I'm going to flip the page and we're going to talk about molecular compounds. So if you still need this, press pause. Okay. Molecular compounds. To talk about the solubility of molecular compounds, we need to go back to a concept that we actually talked about together in early February, and that is polarity. Take a second to think back. What is molecular polarity? So polarity, remember that, is an unequal sharing of electrons in a molecular compound. So if we look at a water molecule, this is where we need to look at our electronegativity. Oh, on the back of that periodic table. So many resources available to you guys. Oxygen has a higher electronegativity than hydrogen, so that means it is pulling those electrons slightly closer to the oxygen atom. And that's happening between the oxygen atom and both hydrogen atoms. So what this means here, this is a dipole. It means that hydrogen is slightly more positive, oxygen is slightly more negative, and my molecular polarity, my overall, would have a negative dipole up by the oxygen. Okay? This is a polar molecule. Now, not all molecular compounds are polar. I could have a methane. I could have a methane molecule, which is CH4. Now here, yes, carbon is slightly more electronegative than hydrogen. So I see that the electrons are being pulled closer to carbon. All my hydrogens are slightly more positive, and my carbon is slightly more negative. But this is symmetrical. All of my dipoles cancel each other out. So this is a non-polar molecule. Another example of a non-polar molecule might be bromine. Okay, here we have an equal sharing. It's the same atom. There is no difference in electronegativity. It's also a non-polar molecule. There's our very quick review on what polarity is. If you're still stuck on it, go back to our first unit. We did a whole note on this. So why does this matter for solubility? Well, the saying goes that like dissolves like. So what that means, polar solvents can dissolve polar solutes. But not nonpolar. That also means that nonpolar solvents can dissolve nonpolar solutes. But not polar solutes. So polar dissolves polar, nonpolar dissolves nonpolar, like dissolves like. This is why if we mix oil and water, water is polar, oil is nonpolar. That's why they don't mix together. Okay? And what happens is in our polar molecules, these dipoles interact with each other to dissolve and surround. So my slightly negative area of water here, if I had another nonpolar or another polar molecule, it would interact with that. Okay? Now there's a very excellent joke. I'm just going to say it. I'm not going to write it. Two bears are walking across the ice. A white bear and a brown bear. The ice breaks and they both fall in. Which one dissolves? The white one. Because he's polar. And so is water. Hilarious. That would have killed you guys if we were in class right now. Okay, so that is part one. That is part number one of factors that affect solubility. Part number two of factors that affect solubility is temperature. Now we need to break this into, again, two parts. If we look at solids in liquids, well, as temperature increases, so does solubility. This is because the higher kinetic energy remember that a higher temp makes particles move faster. That's grade 9 science for you right there. Okay, so the higher kinetic energy actually causes more collision, so results in more dissolving. That's for solid and liquid. However, for gases and liquids, as temperature increases, solubility actually decreases. And right now, think about pump. If you have an open pop can, if you leave it on the counter, but put another open pop can in the fridge, the one in the fridge will maintain its carbonation for longer because the dissolved carbon dioxide in the pop will stay dissolved because that lower temperature. All right? Higher temperature for a gas and liquid, well, it's the same thing as the kinetic energy. If the temperature is higher, the gas particles move faster, and so they leave the liquid. A solid particle is not going to escape a container of liquid. A gas particle might. Press pause if you still need this page. I'm switching it. That's factor number 2. Factor number 3 is pressure. So pressure namely affects gases. Gases are more soluble under pressure. Okay, and we'll go back again. Example, dissolved carbon dioxide in pop. The can, when you get it, is pressurized to keep the CO2 dissolved. When you open the can, releases the pressure, and a decrease in pressure equals a decrease in gas solubility. Another example is scuba diving and the bends. And I'd encourage you to go look this up. It's a really neat biological response to pressure and gas being dissolved in our blood. Okay, and this is gas dissolved in our blood. Our textbook talks about it, but I bet you can find some pretty cool YouTube videos as well. So these are our 3 factors that affect solubility. All right. What we also need to talk about, though, is factors that affect rate of dissolving. And here's where it's different. Okay, solubility applies to the behavior of a specific substance. Factors that affect rate of dissolving is more general lab practices. Or home. You're at home right now making a lot. I'm sure if you went and scooped some hot chocolate powder into a cold glass of water, you're not going to get a ton of dissolving. But if it's boiling, it's dissolving right away, right? Okay. So factors that affect rate of dissolving. This is a quick part. Up 1 is agitation. So this is shaking or mixing. And this increases collisions between particles. And hopefully you're seeing a theme here that more collisions means higher solubility. Okay, between particles of solute and solvent. That's more looking if we're talking about liquid in a liquid or mass in a liquid. More collisions equals faster dissolving. Okay, how else do we speed up a dissolving? Well, we've already talked about temperature. Higher temperature, increases dissolving rate. Well, and we're talking about dissolving. Dissolving is a solid into a liquid. Rate of solid in a liquid. Can you guess why? Based on what we've been talking about? That's right. A higher kinetic energy results in more collisions. Finally, number 3. This is increasing surface area. So think about coarse salt versus fine salt. If we had some rock salt, like the kind that we put on the roads in the winter, and tried to dissolve that in water, and actually many of you have tried to do that for me in previous courses, versus salt that we get out of a shaker and dissolve that, we're going to see that the fine salt dissolves a lot faster, okay? So a higher surface area means more collisions, you got it, between particles. And let me draw you a little picture here. So if I had my coarse salt, which has the same number of particles as the fine salt, but it's all condensed here in one blob, whereas the fine salt, the same number is spread out. Well, if we're looking at collisions, here, the coarse salt, we have to collide with that outer layer first, dissolve those, so dissociate those, and then the next layer, and then the next layer. Whereas here with the fine salt, we have collisions happening with every particle at the same time because they're already split up. So they're more exposed. If you're trying to dissolve a solid and want it to go faster, you need to grind it into smaller particles. Okay? That actually is the end of this lesson. So go ahead and try the textbook questions. If you haven't finished the saturation curve worksheet from the previous day's work, do that. And then come on back when you're ready to learn about concentrations. Thanks for popping in, guys, and have a great day.